Hey class, it's Mr. Hofstad here with Unit 4, Lesson 5. We're looking at the conservation of mechanical energy. So, we need to first have a good understanding of what mechanical energy is. So, mechanical energy, if you remember, mechanics work on machines. So, it's all the energy that's kind of related to machines. So, they move, they lift things up, they have springs. So, we need to have conservation of the three main types of energy that we've looked at so far: kinetic, gravitational potential, and elastic potential or spring energy. So when we're looking at a system that is isolated, which means that it's kind of separate from its environment, right? No energy is allowed to go in or to go out. So the total mechanical energy of a system will remain constant, right? It'll be conservation of energy, it'll be conserved only when conservative forces are allowed to do work on the system. So conservative forces are forces like the spring force and the force of gravity. So mechanical energy will change from one form to another, but the total energy will not change. So conservative forces are things kind of within the system, right? We already have a spring in the system, so if we stretch that spring, apply a spring force or an elastic force, right, that's not going to affect the energy, right? We're just going to be transforming energy within the system. So similar for gravitational potential energy. Non-conservative forces, like force of friction and applied forces, will actually change the total mechanical energy, right? This is when an external force or some external energy is being brought into our system and either adding or taking away from our total mechanical energy of the system. So we have two sets of equations that can be used. The total mechanical energy remains constant. So this one, nice and simple, the total mechanical energy, which is ET, total, right? T here means total mechanical. And at the initial point, our I, initial, it will be the same as the total mechanical energy at the end. So if we add up all of our mechanical energy, potential gravitational, kinetic, we can even throw spring in there. It's not shown here, but there it is. If we have a spring in our system that's changing its energy, we'll throw that in there as well. Right, we'll break it up into all of the types of mechanical energy initially, and all of the types of, excuse me, we'll add it all up in the final. I got some spring allergies going on. Can't complain though. Spring is finally here. So total mechanical energy, initial and final is our first one. Our second would be no overall change in mechanical energy. So here we're doing change of potential plus change of kinetic equals 0, right? If you actually rearrange this formula to have all of the potential energy on one side and all the kinetic energy on the other, right, we'd get the same equation. It's just a different way of formatting it, a different template to work with, right? So the total mechanical energy at the start of the system is the kinetic energy from it already falling and gravitational potential energy from the height it has from the reference. And at the end, we have 0 gravitational potential because we're at our starting reference height. But we've converted that gravitational potential energy into kinetic energy. And when we add them all up, the total initial mechanical energy is equal to the total final, 800 in both cases. Right? And that's because the only forces acting are conservative forces. The only force here really is the force of gravity. Now, there's no force of friction, and there's no applied force on this dropped ball. Right, an example of an applied force would be a hand pushing it down. So the second way, right, would be very similar. We would just do potential final minus potential initial. So 0, negative 600, and final minus initial, right? 600 in both cases. Let's do an example. We have our pendulum. These are quite common for mechanical energy problems. And we have a speed at the bottom of 3.75 meters per second. And we have this length of the pendulum of 1.8 meters. We don't know its maximum height, but that's what we are trying to figure out. So it has some height here, obviously, right? It's higher above this reference height. We'll say the reference here is where we're at the lowest point, where we have our maximum speed. So that's an important point, right? We have max speed at bottom whenever we're working with a pendulum. So this will be our maximum kinetic energy. And we're looking for its max height, which will be the maximum potential energy. So when we assume we have no friction or air resistance, we can look at this in terms of conservation of mechanical energy. We have no external forces. We have no non-conservative forces. Right? There's no force of friction. There's no applied force to this. Only force of gravity acting on it. So we know that the total mechanical energy at the start is equal to total mechanical energy at the end. We'll call this our start, and it doesn't really matter actually. We can call this our start, this our end. So at the start, we have only this force, or this potential gravitational energy, mg h max, because we have 0 velocity. So we have the mass of our pendulum, the gravity constant pulling it down, and the height above the reference, which is actually our max height. Because that's what the question wants us to solve for, the maximum height this pendulum reaches. And at the end, our final mechanical energy, we have 0 height, so 0, right? 0 EPG, potential gravitational energy. Just like here we have 0 kinetic. So instead of having all gravitational potential energy, here we have all kinetic energy, half of mv squared. All right, we're looking for H max. All we have to do is isolate that variable by dividing both sides by mg. And nicely, our masses cancel. We have our maximum height is equal to half m's cancel v squared over, I like writing it with a decimal here, half of v squared over g. Put in our values. Half of v was 3.75 meters per second squared, divided by 9.81 meters per second squared. If we look at our units, meters squared per second squared, right, divided by meters per second squared, we're left with just meters, which is our height. Perfect. We get 0.717 meters as our maximum height. All right. That is our first example of mechanical energy. We had no spring, anything there, which is nice. This next one, we're working with one cart going down a hill and then back up. We'll assume no friction so we can use our conservative forces, conservation of mechanical energy. So we're determining speed at C. What does that mean about B? We can ignore it. If we have conservation of energy, we know that B, right, will have the same energy as A, will have the same energy as C, but we're going to use what we know about A and its mechanical energy to determine what's going on at C. So the height at A is 8.6 and its speed is 4.5 meters per second. And we got at C 5.9 meters of height above our reference height, which is that dotted line right at the bottom. And we want to find VC. Okay, so this is the setup we're working with. So we have no friction or air resistance, so we'll use conservation of mechanical energy. We have our total initial, or I guess that would be at A, equaling our total mechanical energy final, which will be at C. So at A, we have gravitational and we have kinetic. And again at C, we also have some potential, we have some height, and we have some kinetic. So we're going to have to solve for everything that we have enough information for by breaking it up into its formula. So we got gravitational potential energy is mass gravity height at A plus half of mass speed at A squared is equal to mg h at C, which is 5.9 there, plus half of mvc squared. So we're solving for our only unknown there. Let's make our lives a whole lot easier and right away see that we have a mass in every single term. So if we divide everything by mass, we can get rid of that. Easy peasy. Now let's solve for VC. VC squared, we're going to subtract GHC from this side, and then we're going to get rid of the half by multiplying by 2. So we have GHA plus half V squared minus GHC. And we need to multiply by 2 everything, and we need to take the square root to get rid of that squared. Alright, so that speed at C can be found by throwing all of our values in. 2 times 9.81 times 8.6 plus half of 4.5 squared. Lots of math, lots of algebra. Half of 4.5 squared minus 9.81 times 5.9, all under the square root. This gives us a speed of 8.6 meters per second. One big long equation, or you could of course solve for each of those and isolate that at the very end. Depends what you like, if you like doing it all in one step or if you like breaking it into chunks. Both would be correct, both would get you 8.6 meters per second at point C. Alright, we got one last example to take a look at, and this one includes a spring. So again, we have a ramp This time it's giving us a mass, so we'll see if masses cancel out. Probably they won't because they're giving us a mass. They're giving us an initial speed. They want us to determine an initial height. So our unknown here is the height at the start. HI, I'll call it. We have our cart. We're going to assume it's frictionless, and it weighs 0.25 kilograms. It's traveling at 3.8 meters per second. And it's going to compress a spring it's going to compress a spring with 276 newtons per meter. Okay, this one is different, but we're still going to use conservation of mechanical energy. So first we have to make our assumptions. So assume there's no friction on the ramp, no air resistance as it's coming down, and we're working with an ideal spring. Once we have all those assumptions in place, we can look at our conservation of mechanical energy. Still no non-conservative or no external forces. So our total mechanical energy at the start is equal to our total mechanical energy at the end. Here at the start we have potential gravitational with our unknown height, and we have kinetic energy. And at the end, right, we're going to say the end is when it's compressed the spring fully. All we have is our elastic energy. All right, let's break it up. Mass, gravity, initial height, plus half mass velocity at the start squared is equal to half spring constant x squared. Oh, it does give us a compression. Our compression is a 16.2 centimeters. Otherwise, we wouldn't be able to solve it. Okay. So we can put all of our values in. Mass is 0.25. Right. We could just isolate HI and do it all in one step. I'll do it the alternative way for those of you who don't like those big, long, scary equations in one step. So mass, gravity, height, which is what we're looking for, plus half of our mass, again 0.25, speed of 3.8 squared is equal to half of our spring constant, which has to be newtons per meter. So that's what they gave us when they said that the maximum compression is 276 newton per meter. And our x value, 16, we need to convert it to meters, 0.162 meters squared. So we get 2.4525 times our unknown h plus 1.805 joules from our kinetic energy is equal to 3.622. So we can solve for h. It will be 3.622 minus 1.805, right? Just bring that over and divided by our coefficient with the h, which is our 2.4525. And it comes out as 0.741 meters or 74.1 centimeters. As long as we have 3 significant digits, it doesn't matter which of those we choose. And that's it, guys. Hopefully that one was okay. We're just working with a new formula. which you can actually, I think you can find it on your formula sheet. No, this one is not, unfortunately. But we're just looking at mechanical energy total at the start and comparing it to mechanical energy at the end. We just have to remember that mechanical energy can be kinetic, potential, and spring are 3 energies there. All right, see you guys. Let me know if you